Okay, so all right, okay, so we're talking about systems of ordinary differential equations. Okay, so on the surface, you might think there are only just twice as much work. Okay, two dimensions, and therefore, well, you just deal with them separately. But unfortunately, that's not the case. Once x depends on y, or when y depends on x, that's all out of the question. The separation of variables is not possible anymore, and therefore it's not just twice as much work. It is we don't know how much work is involved really. Nonetheless, the good news is that for the computer it is just twice as much work. So if we try to solve the system in some way, their algebra might be complicated, but the reality of computing it is twice as much work. As you can see, there's that this is it. This is what the computer does. It does what we once again call Euler solution. Well, actually, I want to Euler solution. Solution should be in quotation marks. Euler solution, and then you just do it separately for the two variables, and it doesn't really matter whether x depends on x or it depends on x and on y. So it makes no difference for the computer. It just completely know the next step. So it's just twice as much work, and then once you have both x's and y's, you plug them. Okay, so that part is really not a challenge. And then if you were to go on with a high dimension, there's once again no challenge whatsoever. So with 3 dimensions, you have three times as much work and 4 times and so on. Okay, so all right. So nonetheless, we are not going to limit ourselves, just like with dimension 1. We're not going to limit ourselves to modeling and simulation only. But also, actually, we need to understand what is that we are getting. And is it possible to get the exact solution? Okay, so once again, we have the setup that comes presumably from a model, from some kind of model of a phenomenon described about possibly usually with respect to time, and then 2 quantities or more, possibly depends on each other and on time. Well, so as I said, 2 quantities. With respect to the third, meaning that their rate of change, that should be clear, that rate of change of the quantities is with respect to time. That's why we like those deltas so much. They are to the Leibniz notation, so we know with respect to what variable we're doing it. When you have only 2 variables, x and t, say, or y and x, then you know what differentiation is with respect to what variable, the other variable. Okay, but when you have 3, okay, so the denominator is very, very helpful. So these are the derivatives are both with respect to time. These are difference quotients actually. These are the derivatives, and these are the difference quotients. Okay, and then so even though differentiation is with respect to time, the dependence is actually there is no time. So that's no time here, no t here. The right-hand side does not have t here, and once again, as we called this before, we still call it autonomous. So in other words, it's like a phenomenon, usually some kind of a natural phenomenon, and then so why the name autonomous? Once again, I'm going to bring it up. Autonomous because if you're considering natural phenomenon, then we hypothetically, that phenomenon is isolated from the rest of the world. Otherwise, it's very hard to understand what's going on. And so if we are spring oscillating or string or populations depending on each other, once again, 2 populations, no respect for others. So then what is that? Then the behaviors depend on each other, but the setting do not change with time. Okay, so and then especially if it's a mechanical device, then what will change with time? That would be some kind of outside force changing arbitrarily things, and in which case it's not on time. So once again, nothing depends on time. For difference quotients. Okay, so this produces the simulation, right? As we did before, the schematics does not change at all, the dependence between the different parts of the theory. And then we proceed after the limit, as before, we proceed with delta t going towards zero. My derivatives turn, difference quotient turns to derivative, and we end up with two derivatives. And then that's what we else we bring in from any algebra, and possibly if you've seen it in calculus 3, and that is vectors. And so in which case things all really become simpler if you you pay the price for simplification by learning ahead of time what vectors are. Okay, if you right now you don't know vectors, this looks complicated, and this step looks complicated. Okay, this step looks complicated because you have to deal with the new ideas of vectors. If you already know vectors, then it is a simplification. You're already comfortable with doing algebra with vectors, and then potentially, if you did calculus 3, also derivatives, right? So derivatives all of what? And then derivatives of those parametric curves. So that's x and y are actually not variables. Remember, those they're two functions of time. So x equal x of t. That's what behind it. Y is y of t. And then hypothetically, if they were to combine together into vector notation, then I'm using capitalization as I did before, and then it is a parametric curve. And once again, x capital indicates that it is multidimensional. And then once, if you know vectors, you know that there is no extra effort to understand it from dimension 2 to dimension 3. And dimension 3, dimension 4, it doesn't really matter. So that's what makes it worthwhile. Okay, so these are the two functions that we are supposed to find, and together they produce a parametric curve, but separately we can still then substitute into our system two equations, and then the functions naturally are to be differentiable for that to happen. And then and so that's the setup is pretty much identical to what we had before in dimension 1. So once again, this is these are the two. So that's what produces simulation. We already did that. Okay. So time progresses delta t at a time, and x depending on where you are in terms of x and y, the two sort of spatial variables. Then you know where you're going to be next. Okay, so that's the simulation for you. We have two sequences. Okay, sequence for actually for y altogether, plotted together, they will give you what a sequence on the plane. Okay, so just like with the predator-prey model. Okay, so difference quotient, the limit, substitution, so what we already have a few examples of simulations. Okay, so we know that there's something to be explored. So now we're going to in the direction that is towards theory. Okay, and theory is what differential equation is, what the solutions are, existence and uniqueness, of course. Okay, so that's what it is. So x and y differentiable functions are to be substituted into our differential equation, and then presumably you have a function on the left and on the right. They have both functions of t, and this one is of t, and then after all the substitution have been done, and you have two functions on the left and on the right equal to each other, then you know that you have a match, and that xy that you have found is a solution. Okay, there is no difference. The logic is exactly the same. So now, but what is a differential equation, and can we see more to it before we actually solve? Remember that's what theory is, theoretical part. Not much of everything is theory, but the theoretical part, existence and uniqueness, is to begin with. So, which means that we are not trying to solve it. We want to speak a priori. We're looking at the system or vector equation, and then we want to say something ahead of time or about the existence and uniqueness. And so then, what is the differential equation, system or differential equations? And the answer is a vector field. Okay, so once again, if you look at our differential equation, then x and xy. My picture. This is where we are, and here which way to go. That's what it is, and so no matter where we are, we're supposed to know which way to go. To make the setup complete in the sense that it is, will produce some kind of dynamics. So once again, so if formally, that's what we explained. Informally, every point has a vector. Formally, there's a function from R2 to R2. And this is how would you write it if you were to write it in terms of two specific functions, two functions of two variables. Okay, so you can compare it to calculus 3 when you speak of what? Partial derivatives of a function of two variables, and now we have two of them. Okay, so naturally it takes you to the next level in terms of the complexity. Fortunately, we do not need, we're not going to be doing differentiation of these functions. Okay, so these are, in a way, we're going to be integrating them. Okay, so once again, this is the setup. Okay, two functions. Once again, the t's are hidden. So the reality behind the differential equations that are written at the top, system of differential equations is this at the bottom. So it is actually, we're speaking of function, the unknown function that's a t, and then everything depends on t. And so after the substitution is completed, it's nothing but two functions of t. Okay, so that's what we're talking about. And then naturally, as before in dimension one, the properties of f and g are what will answer our questions. So let's once again what we looked at last time. X prime is equal to y prime is equal to x. This is what is an example? It is example of example of what? If you were to go backwards and do the substitution of the not the substitute, but rather go back to what is the model of. Remember what is the model of this system of differential equations? Kind of phenomenon is that? Well, you can probably easily think of some kind of physical device, but populations. If these were two populations, what's the relation between the two populations? They would.
Growth and death.
Well, yeah, but why you look at x prime depends on y it depends on y prime depends on x. So these are two populations that affect each other in what way? Well, that will be a solution. Okay, so let's look at the setup. So to understand, because we didn't do this job usually, model, then differential equation, then a solution analysis. So let's go backwards. That happens too. So if we were to have this differential equation to then what is could it be a model of if once again x and y are two populations? What the effect do they have on each other? Is it positive or negative? Is it predator-prey model? No. So what's the effect then?
As one increases, the other one has to as well.
If one is the larger one, the faster the other one is growing, right? That's the issue equation. It says exactly that, right? Yeah. So the larger one is, the faster the other one is growing, and vice versa, meaning that if the population is smaller, then the other one is growing slower. But otherwise, both of them are positive. So both of them are growing because population cannot be negative. Then the growth is assured for both of them. It is definitely not a predator-prey model or any kind of competitive situation. This situation is a collaborative situation. So once again, maybe two line populations, maybe some kind of symbiosis. Okay, so. What is it? I'll think of something biological system when two species just interact with each other, and the more one gives the help, the other lends a hand to the other.
Like a virus in a city, the more people there are, the faster.
So hold on a second. Yeah, there's one way, but how does it work the other way? how does it help people to have viruses? It's more like,
It's a virus that gives you super strength.
okay. Well, maybe, remember there are little birds that, get into the mouth of a crocodile and help it with his teeth. And what he didn't finish eating, they eat it up, and then healthy teeth for the crocodile, and so everybody's happier with them. You can see a bunch of those, or some, I don't know, maybe some kind of hog, and then there are little birds that go through its fur and find some ticks and so on. So once again, more of one, more of the other. So it's not, they do not prey on each other, so which means that they're helpful with each other in a positive way. So the population of one, they don't compete for food, and they don't compete in any other way. Certainly do not eat each other. So that's the good news. I actually put it in the form of a question here, right here, number two. Two allies, so it doesn't have to be necessarily biological, maybe just two companies or some, I don't know, some populations that help each other. Well, maybe it is division of labor. Literally, you can see it in biology. You can see it in human economics. So these people make, I don't know, spoons, and these making forks. Okay, so they help each other because they're creating a set. Okay, something like that. So this one, number one, that's different. Number A, part A is different because they are both they're competitors. Okay, so not necessarily eating each other. So that's not to say. So to be clear, not predator prey. Okay, so it's not directly eating the other population. It's simply they're eating the same stuff, not each other, but the same stuff, and so that's the competition. So if I eat more, they eat less, and that's bring them down in a different way. So you would have minuses here, right? So the same equation, you can imagine, but there will be minuses on both sides, right? So if x prime is equal to negative y, right? X prime is equal to negative y, and y prime is equal to the negative x. Okay, so that would be the competition, direct competition, not predator prey. So anyway, okay, so how do we solve it? The answer is always to be sure that we actually understand what it means to solve it, and what it means for a function, two functions, to be a solution or not to be a solution. We substitute, and if everything works out equal to each other, we mark the yes, and if not, we mark no. So very easy to find function that do not fit. And then once it is understood that you can jump straight to the solution, and that is the challenging part. And so you have to know a trick, or the trick. In this particular case, is fairly straightforward. You substitute y. Y is equal to x prime, so why not substitute, right? So x prime is equal to y. Y prime is equal to x, which means that x double prime is equal to x. That's the conclusion. And then once you get it, you recollect your experiences with differentiation. And unlike the last example, one-dimensional case, there's a second derivative. So which means that you cannot easily write out the answer as in one-dimensional case, because now you have to solve, even though there's only one function. That's the success of our substitution. Nonetheless, we are not in the position to write the answer as easily, because the second derivative, second order differential equation, we didn't even spend any time doing them, unfortunately. So the good news is that we could recognize some of them, and even though the answer is not sine cosine, because the sine cosine produce negative sign. But there, as I suggested. Did I suggest the answers here somewhere? Well, the one is here already, but also to begin with, e negative x as well. E negative x, which is a different one. So then what else is there? So I'm sorry, not ex, et. Okay. So in other words, one solution is the growth. Both of them are growing. That's what we discovered by accident. And the other one is both are declining. Right? That's also a possibility. So unfortunately, even though they cooperate, once one of them starts to decline, then that it will bring the other one down too. So there is no guarantee here.
Okay, so then, and then the question becomes, where is the rest of them? So have we found all of them? And the answer is not, it's not so obvious. So we just literally have only two solutions. ET, this one, E negative T, E negative ET for all of them. So that remains unclear, but it is certainly will be once again a family of solutions. Once again, the question of existence and uniqueness comes up. Okay, so if we go back to geometry, this is what we're facing. You have vector fields and your solutions that you try to find. You try to find all of them at once. So once again, we're speaking of the solution set. Okay, so a vector field is given, that's on the left, and then so this is vector field, right? And then you're supposed to produce a bunch of curves on the xy plane, each of which is actually a primary curve. And then what are they? They are supposed to follow these arrows on the left are tangents to our parametric curves. Okay, exactly. So it's very similar to the one-dimensional case, except there's more for us to worry about there. Okay, so what I looked at last time is the autonomous equations. In one dimension one, the shift of the graph along the t-axis will not produce new. It will produce solutions again. Okay, so technically it's one solution and shifted infinitely many times along the t-axis. Why so? Because in the equation t is not present. So in the two-dimensional case, the story is exactly the same, except now our curve looks like this. It's actually a three-dimensional thing, but nonetheless the story remains the same because there is no presence of t in our differential equation. Then we can shift it along the t-axis and we'll produce more and more solutions. So which means that we only need one curve, and so we're not worried about finding the rest of that. So if we were to visualize, that's how we visualize it. So x and y are the two axes that we know, and then the t-axis is hidden there, so where it's like the third dimension that we cannot plot because it's on a piece of paper. Okay, so that's a shifted solution. Once again, shift by t. Remember what a shift along the t-axis is supposed to be. It is substitution t plus s gives you a shift along the t-axis. Okay, and they are supposed to be also be solutions. Which means, by the way, so since we have a couple right here, right? So we have ET and E negative t. So we already know from this theorem that it follows that for our model of collaboration, it will be E t plus s as well as E negative t plus s. These are the shifts. Okay, so we already have a bunch of solutions as well that they were not as obvious. Okay, so all right, so that's another. We already looked at this solution. So let's the example. Sometimes the relation between dimension 1 and 2 is sometimes more, it looks more complicated than it is. So remember that always you can go to from dimension 2, you can always go to dimension 1 if you only set that x prime is equal to 1. Then what it means that x is the same as time, and so what's the difference? And then this whole situation, it becomes one dimension. Okay, so I don't know why I have the exact same picture here. Okay, so the solution set does not look like this. It's supposed to look like this. Okay, so in other words, it fills the solution set fills the xy plane. Okay, filled, and once again, in a manner that would be existence and uniqueness. But first, the initial value problem is so this initial condition is a combination of t naught, x naught, and y naught, three numbers. T naught is when, and xy is where. Okay, so maybe two populations that we know here, and then we see which way the dynamics goes on. So that's the once again a very similar write-up here of the initial value problem. Differential equation on the left, the initial condition on the right. So in other words, out of all these, we actually pick one if the solution is if the initial condition is supplied, like here, then only one curve is supposed to be produced. And that is just a way to approach the next two issues, and that's the existence and uniqueness. So we say that an autonomous system satisfies the existence property at a point t x y naught when the IP above has a solution. So once again, the logic is the same. If you have a model of a phenomenon that better off any initial condition should produce dynamics, and if not, then there's something wrong with your model. Okay, uniqueness property is that the two solutions are not allowed to be to overlap, or not overlap, really intersect. Okay, so hypothetically, if we do it one point at a time, the overlap is actually possible. Okay, so because maybe if you're unique here, then and it's non-unique there, so they might separate later. So that's why if we want uniqueness, we want uniqueness everywhere. So even though so one point of uniqueness is not good. Because it then become a non-unique later, and so what we want is all our domain should be filled with solutions in a non-intersecting, overlapping map. Okay, so once again, the logic is the same. If you have two intersecting solutions, it is the same solution, and the picture is the same. Illustration is pretty much the same. So once again, remember this question. So. This is not, okay, this is not what non-uniqueness looks like. Okay, so remember this problem and why this is, I would put it this way. Remember from the one dimension. This is not what non-uniqueness looks like. Why not? Oh, they intersect. So, but I accept non-uniqueness. It's not. I'm not illustrating uniqueness. I am illustrating non-uniqueness. Why would I say this is not what non-uniqueness would look like if we were in the once again in a case of a differential equation, dimension 1 or 2? That makes it non-unique.
Because one's increasing, the other's decreasing.
So, okay, well, actually, it depends on which way your axes are, and where the way I see it, that both of them are increasing, but maybe.
Oh, I was looking from the
Well,
writing.
yeah, but you are on the right track. You might, so there is a mismatch between the two behaviors. Specifically, what's the mismatch?
They have the same slope at that point.
They have different slope at that point where they intersect. There is only one arrow at every point. So if there is an arrow, it is either this one or the one or that one. So you cannot have two. So the vector field, this is my vector field, this is my vector field, and it has exactly one arrow. Okay, so if two trajectories intersect, they do not interject in this kind of crude way, but rather they do it in what way? So if this is a no, then what is a yes? A non-uniqueness. Once again, what does non-uniqueness look like?
There's a section of the curve that matches up.
Well, yeah, that would be that certainly is a fair way to put it like this, but that's not necessarily the there's a simpler case like this. So they can touch. So as long as they touch, the touch means that they remember tangent, literally the tangent is what it stands for. So they have the same tangent, and so that's non-uniqueness. That's what you expect non-uniqueness to look like. They touch. So at the touching point, they have the same, they share the tangent, and therefore there is no violation of this picture cannot come from a differential equation. That's what the problem really is. It's not that about uniqueness, non-uniqueness. It's just it is a trick question a little bit, because the problem with the picture is not that it's unique or non-unique. It's that this simply is not a differential equation. Okay, so no matter what you have uniqueness or not, it cannot look like this because the trajectories never cross in this pattern. They have to cross. If they do cross, they cross it like this. So that's the picture here. Indicates illustrates both of the almost like three ideas here. So an overlap in the middle, okay, so that's uniqueness. And then non-uniqueness is when they separate, and then but they hinge to each other, right? So the red dot where they fork, they hinge to each other. So in dimension two, nothing changes in that respect, so keep that in mind. Once again, we expect curves to behave nicely and they never cross. And so some of the arguments will be made in that respect. So let's take a look at some of the familiar family of curves and see how they produce differential equations of these are my parabolas. Okay, so if last time we were thinking about them as like t and x variables, now this is the x and y. So this is how you can produce the if they're x. Remember what we did last time. You can just the c is the vertical shift. So how do we get rid of c? Just differentiate both sides, and you end up with y prime is equal to 2x prime, which is a one-dimensional case. But this is differentiation with respect to t, not x. So it's not a system. It's not a system, but we can easily produce a system if we just, for example, choose x to be equal to t. Okay, in which case, yes, we have then x prime is equal to indeed that's my system is 1, 2x. Okay, that's the vector field. This vector field will produce the picture. So they go down, then up every time, up and down, up and down. And so that's my differential equation right here. So x prime is equal to 1, 2x. Okay, so it is a autonomous differential equation. So there is no t present. And yeah, so we went backwards from a family of solutions that looks the way we want it to look with uniqueness and existence, and we produce a differential equation for it. Okay, so what we have here, 1 and 2x. Okay, so parametric curves, last example, exponential graphs, a bunch of exponential graphs. Once again, if we were to find a system of ODEs for it, so how differentiation will not eliminate c. Okay, so that's not working out for us. So this in one-dimensional case is fine. In that, so but that's in the two-dimensional case it does not. Yeah. Okay. So well, once again, if the two-dimensional case is present, hold on a second. That doesn't make any sense. That's not right. Okay, so remember we want to eliminate c. Remember how we eliminate c by differentiation, but we have to isolate c first. So y over ex is equal to c, and now we differentiate with respect to t, and differentiation becomes kind of complicated, but nonetheless now. So let me just point it out how it's done, but then we'll just skip over differentiate over t. So I put here. Okay, so then this is also not. Okay, so C is, what is C? C is that parameter that produces more and more solutions. And here it is a similar thing happens in dimension two. And once again, C could not necessarily indicate shift, as in this example, it could indicate, as in this case, look at those parabolas, they actually C indicates the stretch in the vertical direction. Okay, so concentric circles. Okay, so we already know the answer. We had example last time. Remember, how do we get a bunch of parametric curves that represent concentric circles? Or at least the idea of what function are we looking for? What parametric curves? That probably the number one question actually before you writing equations. Ask yourself what are the parametric curves for these curves? So everybody knows the basic equation, x squared plus y squared is equal to r. Okay, that's the equation, r squared. That's the implicit equation of a circle. Okay, but that's really not what we have been doing here, right? We're looking for parametric curves. So in other words, we're speaking of not of roads. These are roads, but our interest is traction. So they depend on time. So you drive on the road, but you can drive fast or slow, and that's why you cannot limit yourself to entirely to just to say these are the curves. We have to describe them as parametric curves as if we're driving on it. So remember
So X equals cosine T Y.
cosine, that's right, cosine T sine V. So if you already are being the radius, so these are the solutions, right? So the solutions of the differential equation we don't have yet. But nonetheless, that's something that that you need to know. Linear functions, quadratic, and exponential. But this one is very important because it's periodic, and the only way to do periodicity is with trig function. Pretty much the only way to do it. Okay, so this is how I could produce differential equation. If you already know what I'm supposed to end up with, I differentiate. I take my equation. C is doesn't matter what C is, R squared or not. When I differentiate, it disappears, and I have a differential equation with respect to one of the variables. But I don't want to go in a kind of a manner that I did over here. Just say x prime is equal to 1, and then hope that it works. But rather I want to come up with something more interesting. So once again, I'm supposed to produce from this what I'm supposed to have. X prime is equal to something, y prime is equal to something. So I have to actually split it. And we already know kind of the answer, and the answer is kind of you could realize that that what has happened is actually both of the terms in what we just discovered right here is actually an indirect application of the chain rule. Okay, so remember that when you differentiate the composition, then you multiply, you have a function, and then multiply by the derivative, you differentiate it, and then the function on the inside is also being differentiated. So this is how it actually happens. If you take x squared and differentiate with respect to t, okay, differentiate with respect to t, with x being a function of t as well, what happens? You have 2x multiplied by x squared. So this is what this is the derivative of this thing is equal to that. Okay. So the chain rule. Okay, and then the second term is also the same thing. So once you recognize that that's what it is, you make one more step to produce the equation that you're looking for. So long story short, there's some algebra manipulation to actually demonstrate what you end up with. It has a one negative sign. Okay, one negative sign rather than two. Remember, we had those either cooperating populations or competing populations. One has pluses, the other one has minuses, and this one has 1 minus 1 plus. Okay, so one population is actually brought down by the other, but not by the first. And so it is in a way a simplified idea of that we have for the predator-prey model. But it doesn't work with population because this one definitely could be negative, and that's why you have to predator-prey model is more complex because you have to have something realistic for populations. Both of them have to be positive, but here definitely it will become negative because rotation is around the origin. So it is something that has this kind of repetitive periodic nature, but not the population unless you do some extra effort to make sure that they can never be negative. So anyway, so that's my differential equation. So once again, can be written for my vector field is this negative 1x, a very simple vector field. You can detect it what it is from these pictures. So they all look like this. Okay, so a bunch of vectors. Once you plot it, you realize that the vector field, you know what dynamics roughly is supposed to be, even though just like with predator-prey model, remember we had kind of a seemingly round arrows from the qualitative analysis. We realized that they kind of form a circle, but we were not able to conclude that the process was periodic because of the lack of symmetry. Here we do have symmetry. So this symmetry, that symmetry, everything is symmetric. So once you start down that road, there will be no spiral. Okay, so it definitely will come back. So that's what a simple differential equation gives us. Where you can fairly easily guess that it's periodic. Symmetry. Okay. And so implicit solution is a circle, explicit solution, explicit meaning a parametric curve, cosine, sine, cosine, okay? And naturally, depending on, you can also multiply by the if you want the solution set, then one solution is not enough, and so then you could have you put R here depending, so R being the radius of your circle. Okay, so either R squared here or R here and R there. Okay, so that's why you'll have all these circles. And so you can test, you can plug it into our differential equation. So that's we're still there. We're still finding all the solutions might be hard. So what we do instead, we're going to be doing analysis of theoretical analysis. Okay, hyperbolus. Let's skip hyperbolus. Also pretty much the same thing. Also, but as you can see, the pattern is different. So they're going this way. So your whole analysis would produce this. As you can see, they're kind of running away from each other. So they're running towards each other, towards the x-axis, but they are running away from the y-axis. And so the behavior, as you can see, by far more weird. Okay, so the trial and error, you can find differential equation for these curves. So existence, so almost verbatim. The existence theorem, the uniqueness theorem, almost exactly the same as we had with dimension one, except there are two functions, but we're saying the same words about it. Okay, so f of g, if they are both of them continuous with respect to x, the x and y. Okay, so then we have existence. So continuity with respect to one of the two variables. So once again, that concept that I do not, I'm not going to elaborate on it, but it surely is mentioned in calculus 3. Fortunately, the idea is pretty much you don't have to do any extra work. You just remember what it means. Continuity with respect to x means that you fix y and look at what you're left with, a function of one variable. That function is supposed to be continuous, and then you do the other way, fix x and look at what y does to it, and so it's supposed to produce a continuous one function of one variable, and that's the theorem guarantees you that we have existence property. Okay, so very simple. That's the whole idea. So we do one dimensional all the way, everything that we can think of for dimension one, and then we do almost exactly the same. Definitions are very similar, setups are similar. Computational parts are similar, the terminology is similar, the theorems are similar or identical, really. Once, if you want to translate this into vectors, that will be not only similar, it will be identical. Okay, so that's the advantage of vector approach, is that once you put it in the vector notation, it will apply to dimension 1 to 3 or any other one. So for example, if I were to translate into vectors here, what's going to happen is so this x naught is a point in the Euclidean space of possibly dimension n, and then we have some kind of open region. Okay, and then what we have is, say, x prime is equal to f of x. This is my vector differential equation. X once again being multidimensional primary curve, and then we're saying that f continuous implies that existence. Okay, so as you can see, except for making f and x capitalized, I have then the theorem itself is exactly the same, almost identical as in dimension 1. And so that's the, if you, like I said, the trade-off is that you have to learn vectors in order to have this freedom of dealing with any dimensions at once, as if it is the same case. 1, 2, or 3, or any other n dimension n, it's the same thing. Okay, so like I said, it is a trade-off. So vectors take time to get used to. Calculus, so we're speaking of vector calculus, really. Same with the uniqueness, except continuity is replaced with differentiability. Same story. Once again, you fix one of the variables and look at what's left. One function of one variable. Is it differentiable? Does the derivative exist? If it does, then on both counts we have uniqueness too. Okay, so naturally, once again, you create a model and then you examine the functions f and g for continuity and differentiability, and then you can tell how good your model is in terms of existence and uniqueness. Okay, so I have a picture here. So remember the picture of existence and uniqueness in dimension one. In dimension one, it looks like a book. Oops. A family of functions that they're not necessarily repeating themselves, but they're feeling this kind of origin into these. It's like a fabric, okay, and then the whole region is made of these infinitely thin threads. So there are no gaps or holes, and the threads do not cross each other. Okay, so that's dimension one. Dimension two, what's the difference? The difference is not big. We allow our threads to come back, that's all. But otherwise, it's the same thing, right? We can do this. Okay, so, but it's still the same idea. So I don't think you can describe it as a book anymore. But then you can have circles if you like this. So it's all possible like this. So I'm not sure what this maybe what is it a tree trunk. You know, when you cut and you have the rings, tree rings, right? Which are not really rings. What are the tree rings? Are they really rings? I think they're spirals. Are they spirals? Are they rings or so? No, they are maybe rings, but they are rings because yeah, so it grows like this. And then because of different seasons, different seasons produce a different color, and that's what creates a ring. So it is circular, but if you cut a piece of it, then the ring might not be necessarily visible, and so you can have something like this. So imagine this like a fancy kitchen table, you know, made of a big piece of wood. Okay, so you can see those fancy, nice patterns that emerge. And then once again, you don't expect them to do this. They never do this. Okay, so and you can have a circle, which in dimension one is not allowed because this is t, and this is y, and this is here. This is x, and this is y. So the t dimension is hidden, and so that's what allows us to go backwards. But nonetheless, so also don't forget the difference. Also, we like arrows to indicate the direction. Without the direction, it's incomplete. But otherwise, it's very simple, and you can turn book into a circle. So I'm not sure what other so this, like I said, is a book, layer cake, whatever the analogy you want to think of, and these are maybe the tree rings in addition to the books and everything like that. So you also can consider tree rings. Once again, tree rings will not intersect, and naturally there are no gaps left. Okay, so if you're looking for a kind of a nice analogy, think about the dimension three that. Okay, so any questions about this theory? So a vector field, if it's differentiable, produces a picture of curves that permanent curves that look like this. That's it. A priori, without solving. Okay, let's do Euler. Okay, so once again, if we already have a system of ODEs, we discretize it. So that's the step. So ODE, and we are discretizing. It's the same thing. So the story is very short, really. Is remember, so dx dt say becomes delta x delta t. Okay, and so then you have delta x is equal to something, and then you have recursive formula. Except now this we're doing for dy as well. Okay, and so like this. Okay, so that's really what discretization is, because you already have somebody did the modeling for you. You have the system of ODEs in your hand, and you're supposed to you cannot solve it. Okay, so you want to model, you want to do simulation, you want to have recursive formulas, and that's how you do it. You go backwards, replacing. Remember how we get from deltas to d's. That's the limit, right? But we can just as well go backwards if we want to. But it's going to be an approximation. Okay, so ODEs, discrete ODEs approximate and now approximated by continuous d's, which one's which? And the answer is depending on whether your phenomena is continuous or discrete. If it is a population, then technically you might say that it is discrete. So population grows by one at a time. And so in that sense, the R continuous or D is an approximation. If it is a physical process, motion in space, motion is continuous, then we approximate it. So, okay, so Euler's method is capable of tracing solutions very close, potentially, to the one corresponding to the corresponding D. This is the predator-prey model. Okay, so this is done with a lot of computation. It doesn't say how many, but I do believe it is. I don't know. It could be 1,000. 1,000 iteration. Okay, so which means you cannot see these are dots. Okay, you progress from dot to dot to dot. This is not a solution that we solve the problem, and so we can certainly plot those curves if we want to. But here this is Euler's method. Okay, and Euler's method produced the sequence, but the dots are so close to each other, so it looked like a curve. Okay, but nonetheless, look at what can you say about it, about the curve. Okay, what do you see?
Doesn't connect.
Well, even if I make a few more steps, it's not going to hit it exactly, right? They already seem to be separated, right? The separation is already visible, so it will pass. It will pass. It cannot possibly hit this exact same spot. And if we instead of making one small step, we could make even smaller steps, so much so that when we come back, it will look like periodic. This one does not look periodic, even though the small the step of Euler's method is very small. Nonetheless, we already can recognize when they make a full circle, it does not hit the exact same spot. It will be going on the outside. Okay, so all right, so let's review Euler's method. This is Euler's method, right? So we have a curve, and then we go on a tangent from it, and which is because we don't know what the curve is, but we do know with the direction. Which let's follow that direction, which is the tangent to our curve, except the picture is exactly the same as in dimension one, except for those arrows. There used to be no arrows. Why not? Because we didn't need arrows, because the direction of the p-axis indicated the direction. Here we hypothetically, this is also possible. It's entirely possible to move to the from right to left. So that's why we need arrows, and we can go in circle hypothetically. But other than that, everything is virtually identical. There's a point, the direction in which we want to go. We make that step as short as possible. So this is really quite a nice picture, actually, kind of some kind of pond, and then which inevitably we jumped to an adjacent curve. Okay, so we cannot, because it's on a tangent, we're up. But the arrow might be minimal. Okay, so this is the unknown purple point where we're supposed to be, and the red dot is where we actually are. Okay, so what do we do next? We just repeat it. Okay, on the tangent, on the tangent, on the tangent. So, and if the smallest step is small, then we can hope that we're gonna end up with a good approximation. So once again, the explanation for this is a best linear approximation, aka linearization of the solution that is unknown. Okay, so linearization of a differentiable function. That's what it is. That's what tangent line is, and we gotta. Next time we are dealing with another one. We are linearization a function that we don't know. Okay, so that's what differential equations are all about. Okay, so all right. Let's plot this. We already did this a little bit, so let's do it again. So we have a differential equation that's supposed to, or not supposed to, we know that it does, produces these parameter curves as a rotational motion. Okay, so the simple motion that from this simple, really simple ODE, you can pretty much go on and produce the the Earth around the sun. That's the starting point. But if we were to go with an approximation, we suppose we didn't know that trick, remember, of the substitution. So what do? We go with Euler. Okay, so we choose the initial condition, we choose delta t. Let's go with one very simply. And then suppose the starting point is x equal to 0, y is equal to 2. In other words, it is right here. This is the starting point. Okay, and then let's plot a curve. Is equal to negative x. Y prime. I don't think my picture is right here. It is wrong. So remember that sine, cosine sine rather, cosine t sine t, this is counterclockwise. Okay, so and these curves are actually counterclockwise, but this one is clockwise. Right, so for example, if I am in the first quadrant, x and y are positive, so x prime is positive, but y prime is negative. Y prime is negative, which means that this is how we're going, which way we're going, and then our actual direction is this. So in the first quadrant, we're moving this way, and that's the opposite. So we actually moving clockwise if this is differential equation. So I have to then, this is a typo, obviously. So then I have to flip this one. Imagine it flipped which way? Upside down. Or you can flip any way you want. It really doesn't matter. So the point is that the analysis that follows is about clockwise motion. Okay, so all right, so this is my differential equation for clockwise motion around the origin. Okay, so and then which we don't know. We pretend to. So then the starting point is I'm plugging in 0 and 2 into my differential equation, and so I end up with x prime is equal to 2, y prime is equal to 0, which is the direction I'm supposed to go. And what direction is that? X prime is equal to 0, y prime is equal x prime is 2, y prime is 0. Which way am I going?
Directly to the left.
Directly to the right, right? No, to the right. To the right. So okay. So and that is exactly increment is equal to delta t is 1. So multiplication doesn't create anything new. So we literally take a 2-unit step to the right. Okay. So and then okay. So and then just as we did before. So this is entirely repeats everything that we've done before. And then we know x1 y1. Hold on a second. Yeah. So this is my step. This is my step. Literally 2 units to the right, from 0 to 2. So then my next location is 0 plus 2 is equal to 2, and 2 plus 0 is equal to 2 as well. So I'm now, if I was at the point 0, 2, now I'm at the point 2, 2. That's my step. Okay, and then I repeat the same thing again. So from initial condition is 2 and 2. And then so these are ones. And then x prime is equal to 2, y prime is negative 2. What's the direction of that? 2 to the right and 2 down. So it's 45-degree slope is negative 1, right? So going that way. Okay. So and then the computer doesn't need all of that analysis, all the picture just computes it. And so that's really what we want. So the next location is 4, 0. 4, 0. Okay, so in other words, we hit the t-axis at which point okay, what happens at that point? Remember that, by the way, we saw that we had an exactly similar example, but in one dimension. And so once we did this, then we did that, and then we hit point, I think, 4, 0. Okay, so this is 2, 2, 2, 0. And then remember what happened at 4, 0, the equation was negative y over t, and then no, t over y, and we got stuck because we ended up with divided by 0. We do not get stuck anymore because there is no division. Look at my differential equation right there. There is no division. So just because x is equal to 0, y is equal to 0 in this case, it doesn't mean anything. It simply means y is equal to 0. What does that mean? y is equal to 0 means x prime is equal to 0. Which way we're going? X prime is equal to 0. Which way can we go? Vertical, right? So there is no horizontal component, which means that we're left with vertical, and then this is my picture here somewhere. Here it is. Okay, so there is no trouble. There is no chasm between the two halves. If that's what I was referring to, this example that we had in dimension 1, and then once you hit y equal to 0, you even if you get close. Remember, we also got in trouble when you get close to the y-axis, and because it starts to behave erratically and might jump away to infinity. Well, that's not going to happen here because there's no division, and my system will just produce, and I'll keep going, even though it's not definitely a circle, but we can hope that if we just take delta t smaller, my curve will be way back. Okay, so but you should be able to easily do the Euler's method by hand because it's just to get a feel for it. Okay, so at our current location and current time, we examine the ODE to find the velocity and then move accordingly to the next location. Okay, so the choice of how far we go down that direction is ours. Okay, because that's the approximation. The smaller that number is, the better it is the approximation. So we have a solution. Once again, this is the equation, which is almost exactly the same as in dimension 1, except we have now two x's, one x and one y to follow, but otherwise everything is pretty much the same. Okay, so yeah, and then this picture, remember this diagram. So you might start, we did, and on multiple occasions, you start with a phenomenon, and then you produce the discrete model first, and then you do the simulation, and then you go to ODE, or maybe you already have the discrete model, and then you want you have an ODE already. So either you then you go backwards. You go backwards with Euler's method, and you end up with a simulation. So it doesn't matter. It's the same thing. Okay, so that's I'm doing the same equation. Okay, but with a smaller delta x, or also h over here. So it happened to be 0.1. Nonetheless, as you can see, 0.1 seems like a small number. Nonetheless, I ending up with a spiral rather than a circle. Not sure if am I going in the right direction. Which one is the direction? Is actually counterclockwise. Clockwise. This is clockwise. So yeah. So it does match what we had. So the starting point, and then this is the beginning, and this is the end. Right here. Okay. So, and as you can see, once again, we're crossing the x-axis no trouble, which is crossing the vertical because x prime over here, x prime is equal to 0. So we're going vertically. And over there is y prime is equal to 0, which means that we go horizontally. Okay, so every time you can clearly see how the two axes are being crossed. And so that's that. By the way, that part is we call the qualitative analysis, right? So which way the arrows point, and then maybe being able to plot them together. Okay, so hyperbolas, once again, this is what you might end up with. Remember, this is once again competing populations, and there's a decay producing a hyperbola. Okay, so you can certainly have more examples. Examples if you need to, a bunch of them. Okay, so let's do qualitative. Once again, very repetition that reemerges. Okay, so a priori conclusions without solving the ODE, just like numerical is once it's not a priori, but not conclusion, but rather those approximations. These are not approximation. They are the drawbacks that we do not have curves. We just say something very general about them, but it is totally 100% true. Oh, it's not an approximation. So if we're saying the graph has got across the x-axis vertically, that's a fact. Okay, so that's not an approximation. Okay, so all right, so okay, so fully accurate but very broad. That's what it is. So let me remind you the analysis that we started with in the one-dimensional case. We started with the with a negative tangent. Remember, negative tangent, the very first example of qualitative analysis was this. And so let's do it again, but this time I decide just to exclude, instead of having x, I have x. Instead of t, I have x, okay? But nonetheless, the picture is pretty much the same. The right-hand side of the equation has to be examined in terms of the sign, and the tangent behaves very simply. It goes plus minus, plus minus, plus minus, and with gaps where the function is not defined. So whenever hold on a second, so pi over two, it's undefined, pi is undefined in pi over two, so technically I have to do this. Okay, so if it's right hand side is undefined, then we cannot have any kind of analysis. But other than that, this is my strict. This is actually double arrows indicate that there's a cut. A cut meaning that there is no curve there. So wherever x equal to 0, rather what y equal to 0, the solution is constant, right? Y is equal to 0, tangent is equal to 0, and therefore we have a solution that is entirely horizontal. And then the curves are indicating that there is a decreasing behavior over here, and there is a increasing behavior over there. Okay, there's a cut, decreasing, constant, increasing, and the other cut. Okay, so that's the basic analysis with nothing, no differentiation or integration of any kind. We just look at the sign of the right hand side function. The right hand side function is equal to tangent, which is periodic. So all we have to do is just to look at one piece at a time, and that piece is negative pi over 2, and then it will repeat itself again and again. And so okay, so that's the qualitative analysis. This is the output of the qualitative analysis of this one-dimensional differential equation. Okay, but now what does it have to do with two-dimensional case? And the answer is we can just rewrite it a little bit and imagine that actually x depends on t and y depends on t. So it's not y depends on x, but rather how about x depends on t and y depends on t. So what changed? There is no change. It's the rest is exactly the same. So once again, the analysis of the right hand side it follows. And then once again on the xy plane, so just as this one is on the xy plane, right? Xy plane, this is still on the xy plane. And once again, we have to look at the combination at our vector field, which is now here. Fortunately, it's very simple because the horizontal component is always equal to 1. So then the tangent of y will give the direction of the arrow. And so that's what it is. The picture on the right does not have arrows because once again it's one-dimensional. So the direction of the x-axis tells you which way we're going. Here we have to do with the arrows, but nonetheless, it's everything goes from left to right. And but the analysis is the same once again. Wherever tangent is over here, tangent is negative tangent rather is negative. Okay, this is negative tangent is equal to 0. And here negative tangent is equal to of y is positive. Okay, so we have drawn. So here is this undefined, and this is undefined. Undefined, and this is undefined. So that's the how we produce an example of qualitative analysis for two-dimensional case from the one-dimensional case. The logic is the same. It's still we are taking the plane and cut it into pieces with what? With wherever the function is undefined and wherever the right-hand side is equal to 0. Okay, so that where the change of behavior happens. So once again, wherever the x prime is equal to 0, moving horizontally, wherever y is equal to 0, we are moving vertically. Okay, so direction. So that's what we need to find. Once again, before this is if you want analysis, that's what it is. So once again, we have our differential equation right here, and we just want to know which way this one goes. Which way? Not a curve, but just knowing which way. And so, depending on the sign of f and g, we can answer that question. So we determine the sign. So x prime f is negative or 0, or it is positive. And so I drew the arrows. Okay, so to the left. No change, and to the right. Okay, I do the same with y's. Y prime is g depending on the value of x, negative, depending on the value of g, depending on the location of the xy plane. I have negative 0 or positive. Okay, and then I just can fill this table with further arrows, for example, like this. Okay, look at what's to the left and above it, and so we are going, like, what is it, southwest. Okay, so that's roughly the direction we're going. Over here, it will be going, down, because there is no change in the x direction, and here I'm going this way. And then over here, I'm going that way. Both are equal to 0, we have a stationary solution, and over here, I'm going to the right. Okay, so, and then over here, I'm going, this way, and here I'm going up, and here I'm going this way. Okay, so, so that's the little table, like almost like multiplication table of the sign analysis of our two functions produces the sign for x prime y prime. There are 9 possibilities, and therefore 9 possible directions that we can go, including no direction, the one in the middle. So that's the picture right here. So, for example, if you put the sine and cosine, this is the analysis. The paths go from, you can do x and y separately, and then just combine them together depending on the x, y. Okay, I think I'll stop here. Good time to just stop, and we'll do this example from scratch next time.